All right, welcome back to this wall of writing. All right, in this video, I just want to talk about the actual change of variables formula and the theorem. Right, so let's do some setup terminology here. Right, so remember last time, well, actually, in the previous example, we set u equal to something and v equal to something, but we had to, in the end, solve for x and y in terms of u and v. So let's say we've done that, set that up here. X is some function of u and v now, and y is some function of u and v now, right? And we can actually write that as a function that takes in two variables and gives you an output of two components, right? So we call that a transformation T, right? And then if we have a sort of multivariable function with multiple outputs, we can take the the derivative matrix of that, right? And this is, if you notice here, this is exactly the matrix we take the determinant of to get the Jacobian, right? So the way you get this derivative matrix, and this will be true no matter how many variables and components you have, you just take the first component, take all its derivatives. In the next row, you take the second component, take all its derivatives. And then if there's a third, fourth, fifth component, and so on, right? But for 2 by 2, it's just this. Right? And then the Jacobian is just the determinant of this derivative matrix, right? So you'll see that xu yv minus xv yu. All right. Okay. And then we can talk about this kind of a function. So this is t is a function from R2 to R2. Let me just kind of say that here real quick. T goes from R2 to R2. This is a comment. We say a function like that is C1 if every component of this derivative matrix here is continuous, right? So it's the same thing as saying all of the first partials are continuous, right? Because now there's a whole bunch of them, all right? So that's the terminology in the statement on this side, right? So let's say we have a transformation. T of uv is x of uv, y of uv. Right? So one of these guys. X is some function of u and v, y is some function of u and v. We just put it together. Right? Now suppose that's C1, and it takes a region S in the uv plane and puts it to a region R in the xy plane. So the way we use that in the last example is we already had the region R, and we found the region S. Right? That's how you'll typically use this. You'll have an R, and you change it up so that you get a nice S. Okay? So now if you take the Jacobian of this transformation, and that's never 0 on S, then as long as the function is continuous on R, and this transformation is 1 to 1, then we can use this change of variables formula, where we replace x and y with whatever they are in terms of u and v. R becomes whatever region it is in the UV plane, and then dA becomes this term here, the Jacobian times du dv. Right? So let's just explain a couple of the things here. T is 1 to 1 on S. Why do we want that? Well, if we don't have that, we're going to start sort of covering things more than once. So imagine you integrated around a circle from 0 to 4 pi instead of 0 to 2 pi, if you have the parameterization cosine t sine t. Right? That's going to wrap you around the circle twice instead of just once. Right? And that's kind of the idea here, is we want t to be 1 to 1, so we only cover things once. Right? So we only cover r once. All right, and then we want the Jacobian to not be 0, because if that's 0, then this integral's 0 over that piece, where the Jacobian is 0. So it's kind of like a degenerate thing here. Like things kind of collapse down and we lose information. So we really want to avoid that. All right? So this is the main formula here, what we'll be using. I do want to write this one more way now. That just is a little bit fancier and it involves the t. Right? So we can also write this down as the double integral of S of f compose t right, times the absolute value of the determinant of the derivative matrix du dv, right? So I just want to write that down because it kind of shows a little more, and a little more generally, what happens, right? So it doesn't have to be a double integral. This can be triple, quadruple, as many integrals as you want. And I mean, even this formula, continues on. You'd have z of, I guess these would all be UVW maybe, and you'd have a bigger determinant here, but this formula does generalize, but it's written here for just two variables. Right? So this here is, if you like, this is a function of u and v. Okay? Right? So hopefully that all makes sense. I guess the key takeaway here from this video is this is the formula you're going to want. This is how the change of variables works. Okay? See you in the next video.